day 7, and I've still got COVID. I'm still testing positive anyway, which is annoying. But don't worry, we've got a great challenge today to take our minds off it. And basically, software engineering is over now. We're into the computer science era. It's time to do science on Advent of Code. I decided to bring a prop, so I'll be wearing my glasses today. It's an old prescription, so it's going to make things extra challenging. But if you're doing science, you've got to show up. So let's figure this out. So we have a directory structure illustrated here, and our job is to parse a log of this nature and identify all of the directories which are over 100,000 in size, 100,000 somethings in size, probably bytes or something. And for this, we need to sum up the files in the directory and also in any of their subdirectories as well. So we have to do that. Let's look at the input. Oh yeah, we want to see the total size. That's what we want to see. Yeah. So, how long is it? It's kind of long. This is like, yeah, anyway, it's long enough for us to worry a little bit about what we're doing. And we can probably assume that the directories won't change in the process of us going through them. We cannot, I think, assume that we're going through them in any particular order. For example, in here we can see we're CDing into this, and then maybe we are going in some order. Well, we appear to be. Yeah, we appear to be kind of going through in an order. I wonder if that's guaranteed. That'd be kind of nice to know. I don't know. I don't need this. No way. Those aren't. That's a dated stereotype. Yes. Puzzle input, where is it? It doesn't guarantee us that it's in any sort of useful order, but it could be. But it doesn't guarantee it. So we probably shouldn't assume it, sadly, as tempting as it might be for us to just assume that so for example, in this case, if we are CDing into every directory, then we could just sum up so that essentially the sum of the files in this directory, we could treat it as a sort of like stack of directories. Or could we, anyway, we could treat it as, if we knew it was in a sensible order, we could treat it as like we just need to we need to count the number of CDs and the number of dots. And so we could then, when we get back down to 0, we could just sum up all the numbers in that list. And we could kind of recurse on that nature. And that would be that would mean we wouldn't have to have any intermediary structures. But we don't get that guaranteed. I really don't think. No, we don't get it guaranteed. It could not be true. And we don't want to take, because I've only got half an hour, I don't want to take that risk. So but it might be a nice extension exercise. Extension exercise for myself. Come on. I'm supposed to be doing this in a reasonably short time here. Okay. Let's open up Excalibur and have a little diagram around. So my first thought is that we should go through this and translate it into this sort of a structure. And then essentially recurse through this, or walk through it, maybe. I think that's the thing. And then we end up with, we could walk through it and just aggregate all the sizes of directories that are above such and such. So I think yeah, so they can be inside each other. We can essentially duplicate. Yeah, and so then we go to we get the number, which in this case would be, well, we're not given it. This. So it's built, we build this intermediary structure and then we kind of work with it to get this number. So we've got essentially two parts. We've got a something like that. And we've got log tree. We've got these two transformations. And assuming, I mean, is there any way to avoid this? I mean, can we count on all the files having unique names? I'm pretty sure we can't count on that. It's exactly the sort of thing they'd put one of in to really screw with you. Yeah, so I don't think there's a way of avoiding building up this intermediary structure. Not that we can really count on. But we can discount. We don't need really to store the files. That's interesting. I mean, does it matter at all? I mean, why wouldn't we want to store them? It won't really save us any processing time. We can ostensibly, if we don't need to store all the files, we still need to recurse through all the directories, because the most deepest nested directories will likely be the smallest. Well, they will be the smallest. So we're going to need to go through into all of those. We won't necessarily need to. No, we will need to. We actually will need to go through all the files. We don't necessarily need to store them, but there's no good reason not to store them, I think, because we might need them in step 2. And if we do, it'll be annoying to write that. And I don't think the performance implications will be that difficult. So if we look at the kind of worst case performance here, we've got to go through each of these, and we've got to be building up a structure. The structure is not well, it doesn't really matter how deeply nested it is. We can probably handle it. It doesn't matter how big it is. I don't think it can be bigger than the log, strictly. And the log is big enough, small enough to fit in memory, of course. So log to tree should execute in linear time, and then tree to summed 100 or less integer should be executable in the number of items in the list there are, which can strictly not be more than the length of the list. So it's not going to be, there's not going to be a performance problem here, I'm pretty sure. So I think we should just take and it's also only day 7, so it's not going to be anything, probably not going to be anything super horrible. Okay, I think I've got a general approach. I think we just got to do it the blunt way, which is going to involve. So let's look at log to tree first. Guess that comes first. Always. Yeah, I guess it does. Okay. Okay, so that's just like a push and a pop. I don't think, okay, let's look at what CDs allows us to do. CD means change directory. X. Ah, ha, ha. Now, do we get this more than once? No. Trying to trick me there. So we only get it once. So that's fine. We don't get any fancy stuff. Yeah, okay. Okay. And so if we look at the structure, which we're going to just diagram out as Okay, let's do it like that. Okay. Okay, anyway, we're going to need, anyway, so that's, okay. So this is the empty structure. Empty structure. This one's going to be, or actually, maybe it should be, oh, it doesn't really matter, does it? Just looks nicer. Do we care about the names of files at all? They don't appear to mean anything. Well, there's no reason not to store them, I suppose. Okay, so there's this CDA. Now we don't have to decide which directory we're going in. It's already given to us, so we don't need to store what directories we've been to or not. Although it would be interesting to know if there are any repeats. Hmm. Oh no, that's not a repeat. Well, if there are repeats, there aren't a huge number. So that's fine. I guess we can probably assert that that we don't visit the same, if we even care. I mean, I don't, let's just not ignore that. Let's just ignore that. Okay. Okay. In interest of time, let's think about an algorithm here. When line is CD, set current to set current to N, and then when line is LS, go through lines until dollar starting, then add item to current. How do we get the next directory up? We need a stack, I think. I think we do need a stack. So we do need a present working directory. And it would be simpler to just have that. Yeah, so actually we should be add into remove one from present working directory, add item to tree at path in, yeah. Yeah. Okay. Then, is there anything else? No, I think that's it. Yeah, that's all the commands. Apart from cd slash, which is, can we ignore it? Yeah. If think of it only comes at the beginning, that's fine. Okay. All right. So that's kind of that. And I just want to have an idea as to how I'm going to model the tree here. So I'm going to have, I think I'm going to have I'm definitely going to have an item data class, and I'm going to have I'm going to have a file data class and a directory data class, and file is going to have name, size, directory is going to have children, add, or it's like add list, sum, in which case, it's this one that's challenging. And a get with a name. We don't actually need to store directories really, but anyway, get name, and then we can call get name repeatedly in order to get the directory that we want. So we could keep track of two pieces of state, present working directory and directory, and we need to have these both updated at the same time. So we could model this as current directory or path. Yeah, we can model this as path. That would work. Yeah, okay. So in terms of an action plan for this bit, we've got create file, create directory, create path. It's got to have a and then a directory. And it's got to take the root as its argument and then base. Well, actually, if we have directories being given the link to their parent, would that simplify things? I sort of hate classes knowing about their parents. It like bugs me, but would it solve this more cleanly? In the process of creating a directory, we could give it a link to the parent. And then going up a directory would just be as simple as calling parent on it. That probably would be simpler. Okay. So it's going to take parent and it's going to store that. We could change this to size. And size would be polymorphic on both. And will we still need get? Yes, we would. Call this all. All right. Okay. We're starting to eat into our half an hour here. Is it the case ever the directories and files have the same name? No, I don't. I think they've all got extensions, right? So that will save us. Okay, fine. And the loop will involve us going through, asserting on, could use a regex to match against each of these lines. And then if it's an ls, we can take next line until it's okay. We don't know when we've got the last line. And Okay, Python read file, go back one line. Okay, so we can tell and seek. That's good. Nice to know. Okay, and okay. That's kind of an annoying approach. Oh, no. So annoying. Ugh, okay, fine. Well, we'll just do all the matches at the start. Or we could just if on the beginning. Yeah, we could if on the beginning and then use a regex if we need to extract the directory. And then a regex, well, we just need to split here. It's not that hard. We just need to split here as well. Actually, we don't need a regex at all. Okay, fine. Okay. Um, and do we need like a parsing function for this? No, I don't think it will actually help. I think we just split on strings and then split on space and then just condition on one if it's a, yeah, that's fine. Okay. All right. Okay. Then this one, not even done yet. We're 37 minutes into this recording. This is going to be a epic one, and I'm going to have to code fast. Okay, so say we've got this structure. At this point, we need to go through every directory. Ah, wait, is this the trick in here? Is there a comically large number of directories or something? Like, does the nesting yield a really long number of directories? Okay, let me not discard that thought. We could find ourselves, if it was a lot of nested directories, repeating calculations a lot if we didn't do any caching. That's what I'm worried about. If we had like 30 directories deep, then we'd end up with the top one taking like a huge, like it could get really big. So we want to make sure that we're caching the size. We shouldn't call size until we're done working through the directories. So when we do call size, we can memoize it, or we can calculate the size at the end of ls and then sort of say seal it at that point. Okay. Well, we could only calculate the direct size. We couldn't calculate. We need to know all the directories before we can calculate the size of any upper level directory. Or we could throw this whole thing away and just treat this as the data structure. And no, we're not doing that. That would be too. I'm not doing that. Yeah. So essentially, the process here is one, make a list of all directories. Two, call size on all directories. Three, filter on which will call recursively and cache. Filter on size is at most 100,000. Okay. Am I going to get this done in half an hour? Good question. I'm definitely going to. I've got faith in myself. Yeah, I can do that. Yeah. Okay. All right. Let's get set up. Got the input. I'm going to get my sample input as well. This could be the first loss today. This could be the first loss. Okay. All right. Copilot's turned off. Time to get started. Okay. Python, we're in Python. Okay, that's that one. Are any of the directories going to be very big in size? They all look quite small to me. Okay, so I don't need to think too much about that. Okay, fine. Got parent. Okay. Let me just test this out a little bit. Right, anything else we can do? This should be an item. But I'm not going to implement equality, which is going to screw me over. Okay, I'll have to ignore that. Name and size. File. Okay. Name. Okay. Okay. What will it actually be? 5 plus 6 plus 7 plus 8. 26. Okay, great. Okay. Now let's split the line on spaces. We can say if line Okay. Anyway, if line 2 equals slash okay, if line 2 is dot dot, else current is current yet line 3. Okay. If it's ls, we need some different logic. So let me start printing stuff out actually. Go cd root. Okay. Now with ls, we want to do something different. We want to while true line file read line ls line, and we want to say file, what is it, tell. If ls line 0 is a $, we need to file peak save point and then peak seek, and then break, which we can break out just once, I hope. Okay. Else current add ls line 1 is directory, that's line 2, and the parent should be current. add is real. Oh, right. Okay, fine. So it's telling me, okay, I think that's fine. I think I can ignore that. But ideally I wouldn't. ls line, else rather, current, add directory, no, file, ls line, no. If it will be 0, 0, 1. This would be 1, 0. Oh my gosh, okay. Okay, so what are we doing here? Oh, so we're at the end of the file, which is, yeah, okay, fine. Oh, it'd be so nice if we could print this. Okay. All right, well, that's my lesson learned. How are we doing for time? Oh, okay. Not so long now. All right. What are we looking for? 584. Okay. Total size directory is, yeah, fine. 584. Okay, fine. Okay, I think that's good. 584. Yeah, 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 yeah. Okay. All right, we're on 7, 8 minutes. We're on 8 minutes. All right, we can still do this. Okay. Get all directories. Well, let me just do this in script terms. Okay, I'm getting stressed now. Does it extend? Extend, yeah, it is. Yeah, I need another method on here. Mm. 3, is that right? 3 directories. 1, 2, 3, and the top level. All right. Okay. Ooh, getting close. And then is that most this size? Oh, great. Oh, yes. Integerize it. Integerize it. Integerize it. Size. Okay, now what is it actually? Come on. Okay, it's the right answer. Let's try it with the real. Okay, moment of truth. Two minutes, 24 seconds left. Oh my gosh, that was close. Okay. All right. All right. All right. All right. Okay. The total disk available in the file system is 7 million, no, 17 million? 70 million. To run the update, you need unused space of 30 million. You need to find the directory you can delete that will free up enough space to run the update. In the example above, the total size of the outermost directory is that. The unused space must be, well, the opposite, which isn't quite right. Therefore, the update still requires a directory with the total size of at least this many to be deleted. You could delete any of these. Directories E and A are too small. Deleting them would not free up enough space. However, directories D and root are big enough. Between these, choose the smallest. D, increasing unused space by something, something. Find the smallest directory that, if deleted, would free up enough space on the file system to run the update. What is the total size of that directory? Okay, so a few notes. We have a total space of 70 million, and we need 30 million. And we want to find all the directories that are okay, so we need to. So firstly, we need the total size, the total space used in the root directory. Then we need to work out how much free space we have. Based on that. And then we need to work out, therefore, how much space we need. And then we need to work out all the directories that are bigger than that, and then the smallest one of those. So fundamentally, we've got the information that we need. So we're not going to be in too much trouble here, not like the last step. Okay, so first work out currently used space. subtract currently used space from 70 million to get free space. Subtract sorry, my head's a little bit fried now. Subtract. So essentially, like, get the difference between free space and needed free space. Find all directories smaller than this would be better if I just gave these things names, wouldn't it? So let's say currently used is, we've got to calculate that. Then it's not really code. Free space is 70 million minus currently used. Needed free space is 30 million. So let's say total space is 70 million. This total space, yeah, and this needed free space. And so we want to get free space, no. Space needed clearing needed is free space, which should be bigger, less needed free space. Okay. Then once we've got get clearing needed, find directory smaller than clearing needed, get biggest, no, smallest one. And I don't want to have any weird off by one things here. But if I do, it's probably not so bad. I'm not going to spend 30 minutes puzzling that out, am I? Okay, so in the example, the total amount of used space is this number. So to get, okay, so the final formula is this less this. So it's total space, which is 70 million minus currently used space, which is, actually, let me type this in here. This will be more interesting. 70 million minus this number. And I'm just love a bracket, and the needed free space is 30 this. So the total should be Okay, I've totally done it the wrong way around, haven't I? 8381,165. 8381,165. Okay, great. Well, that's right at least. So actually these terms need to be the other way around. Which gets us this, which gets us 8381,165. And then we're looking for directories that are smaller or equal to the clearing needed. Get the smallest one. Okay, so plan of action is get size of root directory, get clearing needed based on formula. 3, find all directories less than or equal to clearing needed. Get minimum of. Okay. Mate, that was off the chain. Oh, I've done it wrong. Yeah. So let's copy all this in. And we don't need, we can have them sized actually, but we could then get trial structure memo size, which is this number. So total space, actually, with trial. Total space is 70, 123, 123. Space, needed free space is 30, 123, 123. Currently used is this. And so the clearing needed is needed free space minus total space minus currently used. So for the trial, that's not right. Oh, we haven't printed it, that's why. Okay, still haven't, oh, I'm running the wrong file, that's why. Yeah, there we go. 8381165. Okay, fine. And then we want to find, we don't actually need these anymore. Is less than or equal to clearing needed. And we want to find the smallest. How many are there? Only 2, fine. No, it's gonna print. Oh, I've already got it. Right. Well, that's clearly wrong. Oh, greater than or, yeah, okay, that's why it's small. Okay. Is greater than or equal to. Clearing needed. And then we want to get the minimum, which is the min of this. So that's 249,33642. 249,33642. Okay. Great. In which case we can switch to input and get this number, which is bigger. Okay, let's switch to this. Okay, 2543. Well, that was a thrill ride. All right. Reflections. One, it's the end of a long day. Two, obviously this looks horrible, but I think the classes and files, I think they panned out as a decision. I don't think I would have managed it without that. But I suppose I could have, if I was better at procedural programming, I guess really this is just a, it's not, I mean, you could do it with bare data structures, and you could do that. But then again, this didn't take that long, I don't think, to write all of this stuff. I think that was relatively straightforward. I think this parsing and getting this right did throw me a little bit. Well, I guess I'll watch the recording. And I think I got a little stressed at the end. I think my plan was good. I don't think I'm going to learn any more right now. Right. See you tomorrow.